Hello, my name is Ulises Maldonado. I am a mechatronics engineering student at the Tecnológico de Monterrey University in Mexico City, and this is my submission to the Altair Global Student Contest. This is the part I choose. It is a pulley for the transmission of a car that competes in the Shell Eco Marathon with the goal of achieving the highest possible energy efficiency. I choose this part because when aiming to improve energy efficiency, it is crucial to reduce the weight of the vehicle as much as possible. The belt consists of a tension strap that transmits energy from the motorized pulley to the driven pulley through the friction that occurs between the belt and the pulley tips. I will analyze the part using Altair Inspired version 2022.3.1. I will conduct the analysis through a topological optimization with the goal of reducing its mass by 50%. This is my finished part with its loading conditions. For the FEM analysis, the general boundary conditions were the maximum torque the pulley will receive in both directions, and the fixed point where the pulley anchors. The maximum obtained torque is 24 newtons meter. It is set in the faces of every dent the pulley has, and the anchor point is set in every contact the pulley has with the wheel hub. Also, I selected plastic ABS as the material for the entire part since it will be 3D printed. Let's review the results of the initial analysis. As you can see, we can observe how the part moves in an exaggerated manner for visualization purposes. And we can view both forces conditions together or individually. Also, we can observe its both misses, stress, and most importantly, the safety factor of the part. By using the filter, we can determine that almost everything has a safety factor greater than 6, indicating that it has potential for optimization. This is now my part ready for optimization. I create a partition for the central part where the pulley attached to the wheel hub and another partition on the outer perimeter where the pulley tips are located. I convert the interior area into the design space where the volume of the part will be reduced. For shape control, I added a double draft which has a demolding direction from the central plane parallel to the part towards both outer sides. The goal is to concentrate the material in the center and make it easier to 3D print. I also applied cyclic symmetry control to achieve a pattern repeat 4 times around the part, providing a visually symmetric shape. I choose to optimize for maximum stiffness to control the percentage of mass reduction in the design space. And after some tests with small variations in the parameters, I decided to set a mass target of 20% and a thickness size between 10 and 25 millimeters, applying both load cases. And this is how the optimization turns out, taking around 2 minutes. Finally, to ensure proper functionality, I conduct an analysis of the optimized part. The displacement doesn't change much, but we can observe an increase in stress, which is normal. Also, the safety factor, it changes, but we can see that the entire part still has a safety factor greater than 6, ensuring safe use for its intended purpose. When comparing the results, we can see that it started with a mass of 0.33 kilograms, and ended with a mass of 0.15 kilograms, resulting in a weight reduction of 54%, which is great. To finalize the optimized part, I applied a polynerve, and this is how the finished piece looks, ready for printing, featuring a smooth and consistent form. This is my submission. The part turned out well and functions smoothly. I enjoyed working on this piece, and I learned a lot from both the software and its capabilities, as well as the parameters and techniques from optimizing a part without compromising its functionality. Thank you very much for listening, and I hope you enjoyed it as much as I enjoyed the process.